Good morning, everyone, and welcome back to Math 115. So today, we are going to talk over the last little bit of section 1.9, and then we're going to start chapter 2. I have not yet posted the chapter 2 skeleton notes to Blackboard. I'm a little behind on writing the notes, but I'll post them maybe after class today. And yeah, you also have some homework assignments coming. So I assigned 1.8 over the weekend. It's going to be due on Tuesday. So Tuesday night, 1.8 will be due on all of the different, what is that? That's compositions of functions, right? So 1.7 was already due. I think that was due yesterday. Okay, so that's the homework that's coming. I'm also going to post a homework for what we talk about today that'll be due later this week, probably on Thursday or Friday, maybe. Your next assessment, okay, is going to be quiz number 4. Quiz number 4 will be 1 week from tomorrow, okay? So you have 8 days until this quiz on Tuesday of next week. So since that quiz is on a Tuesday, the best time to come to my office hours and study for that quiz is going to be on Thursday this week. Okay, on Thursday this week. So I'll announce the content that's going to be on the quiz on this following Tuesday, no later than this Thursday, so that you can all come to office hours and ask questions about those relevant homework exercises during office hours this week. Does that sound good? Okay, so speaking of office hours, as always, I'll have them from 2:30 to 4 p.m. in my office, LeConte 439, unless we change rooms because we have too many people. So that's not today, that's tomorrow from 2:30 to 4 in my office. And the tutoring center is available at all times. So if you want to get help on the 1.8 homework, but you can't come to my office hours, or it's just not a convenient time for you, then you can go to the Math Tutoring Center in LeConte 102. You can take your homework there from 10 a.m. to 4 p.m., Monday, Tuesday, Wednesday, Thursday. Okay, so that's a very wide window. And you can go there and get help with your math homework. Has anybody gone to the Math Tutoring Center recently? And can you report what was your experience like?
Oh, it was very nice. He was extremely helpful.
Okay, so I'm hearing very nice and extremely helpful regarding the Math Tutoring Center. So go there. Make sure you make use of that resource because it's super useful. All right, any administrative questions before we start in on content for today? All right, doesn't seem like it. So let's review what we talked about last time. So last time, I can hardly remember. Oh yes, we did do this last time, didn't we? Or did we do that the time before? Anyways, I think I can, let's re-explain this just because it's a difficult topic anyways. Okay, we talked over compositions of functions. I think we did do this last time. We talked over the addition and multiplication and division of functions the time before, but but the last time we were in class, we learned about the compositions of functions. So we plug one number into the first function, and then we plug that number into another function, okay? So the whole process looks like this, okay? Our number goes first into the g function, and then out pops g of x, and we need to plug g of x into the f function. Okay, so when we were talking about the domain of a composition of functions, I drew this really horrible looking diagram that's really confusing, but let me see if I can explain it in simpler terms. Okay, if we want to talk about what sort of number x are we allowed to put here? What sort of numbers am I allowed to put here? Well, I need to consider two things. The first thing is that x needs to be allowable as an input for the function g, right? If I can't even plug x into g, then I'm really screwed, right? But what else do I need? I also need, after I plug x into g, I will get another number. Yes? And that number needs to be allowable as an input into the function f. Okay? So this is why the composition of two functions, we have to be a little bit careful with the domain, okay? So we need values x which can be plugged into G, and moreover, when you plug them into G, you get an input which is allowed to go into the function f. Okay, so that's the only deal with the domain of a composition of functions. So this diagram was really just trying to show you what's going on there, is that, look, if our number can make it through G, and then also the number that gets output can make it through f, then we're happy, yes? But if the number is allowed to be plugged into G, but that number is not allowed to be plugged into f, then I'm in trouble, right? Or if there's a number, for example, which is in the domain of f, okay, I can plug that number into f, but there's no value G which maps to it, right? That's another issue. Okay, so that's about the domain and, the domain of a composition of functions. And then the way we find the range is the same way we find the range of any other function. We just check what is the total set of outputs which we could achieve by plugging in any number which is in our domain. All right. So that was domain and range of compositions. And then we started talking about inverse functions. So for inverse functions, we wanted to have a way of undoing a function, right? So if I have a function which does something, it would be nice if I could reverse that process. The only hang-up is that I can only reverse the process when my function has a very special property. And that special property is called one-to-oneness. Okay, so if our function is one-to-one, then it can be inverted. Namely, we can find the inverse function. However, if the function is not one-to-one, for example, this function here is not one-to-one because it fails the horizontal line test. You can tell that my avant-garde abstract pencil here is touching the graph at 1, 2, 3 points. Therefore, the horizontal line test is failed, and therefore the function is not one-to-one. If the function is not one-to-one, then it can't be inverted. Can someone give me a brief explanation of why we can't find the inverse function if our function is not one-to-one? Sorry?
Isn't the same thing?
Isn't what the same thing?
Like if you inverted it.
Well, loosely speaking, if I inverted this thing, okay, I would get a function which does not pass the vertical line test, which if it doesn't pass the vertical line test, then it's not a function, right? So the problem is, my question is, I ask you, what is the input associated with this height? What is the input such that the output is this height? And you say, well, there's this input, and there's this input, and there's this input, right? So there's a flaw in my question because I asked, what is the input such that the output is whatever this height is? Let's say this height is 2, okay? I ask you, what input gives me height 2? And you come back at me and say your question doesn't make no gosh darn sense because there's 3 different inputs which all give that output. And the way I asked my question, I said, what is the input? As if there was only one. But there are clearly 3, yes? So this is why our function needs to be one-to-one in order to ask about the inverse function. Okay, I'm getting the sense that's a little bit confusing. Am I right? Okay, so maybe I can try to explain using another method. One thing that's true is that if you take the inverse function, what you will get if you invert the graph is that the function will be reflected about this line, y equals x. If you were to do that, God, this is not going to be good, but let's try. Let's try anyways. So if I reflect about that, What's it going to look like? It's going to look like this. Yes? That's what it would look like if I reflected it about that line. Okay? You see how I took it and I flip-flopped it like that? So what's the problem with this curve which I've drawn in the plane? It fails the vertical line test. So if we're talking about the inverse function, keyword being function, well, we have an inverse here, but it's definitely not a function, right? Because it fails the vertical line test. Okay, so that's one more interpretation for you. All right, so algebraically, what this property means is that if the inputs are different, then the outputs are different. If the inputs are different, then the outputs are different. Okay, so here's an example of all the inputs. Okay, here's x1. There's no way that we're going to have an x2 which has the same output, right? Because this is an increasing function. It just keeps going up. All right, so that's a one-to-one function. All right, so we talked about the horizontal line test already. Okay, so now let's talk about... Oh, yes. Okay, so then we defined what is the inverse function. Okay, so the inverse function, I really don't like this white color. I'm going to have to change that later. The inverse function is defined so that if I have a given input, x, and if I plug that into the function, I get y, then if I take y and I plug it into the inverse function, it will give me back the associated input, which would give me y if I were to plug it into f. Okay, so f of y equals x instead of f inverse of y is equal to x if f of x is equal to y. All right, so the domain and range are pretty simple. The domain of the inverse is just going to be the range of f, okay? And then the range of the inverse is going to be the domain of f. Okay, so that's what we talked about last time, and I believe I stopped there. So are there any questions about what we discussed in class last time? All right, it doesn't seem like there are, so let's see how we actually find this inverse function. Okay, so let's say we have a function, and supposing that we know the function is one-to-one, we want to try to find the inverse. We want to try to find the inverse function. Well, we can do that just fine. There's no problem with that, and here's what we do, okay? What we are going to do is rewrite. We know that this f of x is equal to y, yes? Because that's how we get the height of the function on the graph, right? So we are going to take y equals 2x plus 3. And here's what I'm going to do. I'm going to replace all of the x's with y's. And I'm going to replace all the y's with x's. And then I'm going to solve for y. So let's see how that works. So I'm going to change this equation and get a new equation. The new equation is x is equal to 2y plus 3. And now what I need to do is solve this equation for y. So how would I do that? I just subtract 3 from both sides, and I get 2y equals x minus 3. And then I'm going to divide by 2. So I get y equals 1/2 x minus 3/2. And this is the inverse function. So let's check that this inverse function has the properties that we say that it does. So let's try f of 1. Let's see what we get if I do f of 1. If I do f of 1, what am I going to get? I'm going to plug in 1 for x here, and I would get 2 plus 3, which is 5, yeah? Yeah, agree? All right, let's see what happens if I do f inverse of 5. I should get back 1, yeah? So let's see. If I do f inverse of 5, I get 1/2 times 5 minus 3/2. Okay, so that's the same as 5/2 minus 3/2. And how do I subtract fractions again? I just subtract the numerators, right? and I keep the denominator the same. So I get 2 over 2, which is in fact 1. Okay, so check that out. We came up with a function that reverses the process. If I plug in the output of the f function, then I get back the input. Okay, so why is this relevant? Well, you could ask 2 questions, right? If you have a function maybe that describes like the profit that your company makes if you sell a certain amount of product, right? There's 2 types of questions you could ask. You could ask, if I sell this much product, how much profit will I make? Right? That's one type of question. But an inverse type of question would be to say, how much product do I need to sell in order to make a certain amount of profit? Right? So this is why inverse functions are going to be really applicable, at least in like a workplace setting, for example. Okay. So any questions on how I did this, found this inverse here? I just replaced x by y, replaced y by x, solve for y. Okay. Then, let's talk about the properties of the inverse function. Well, let me ask you all, what do you think is going to happen if I take a number x and I plug it into the function f, and then I take whatever I get out of the function f and I plug it into the function f inverse? What do we think we're going to get when we do that? Yeah, just x, right? We just did that with 1 and 5. If you take f of 1 and you get 5, right? Then f inverse of 5 is the same as f inverse of f of 1, right? And we can tell we got back 1, right? So when we plug a number into the function and then we plug that number into the function which undoes whatever our original function did, then yeah, we're going to get back what we started with, right? Okay, and same deal if we do it in reverse. Same deal if we do it in reverse, okay? F of f inverse of x is just x. So sometimes, for shorthand, what I'll do is I'll kind of describe, well, these 2 processes undo one another, so I can just kind of cross them out like that, and I'll be left with just x, okay? Something like that. Okay. So what's next? Well, if I have a function g which satisfies these 2 properties, okay, which satisfies these 2 properties, namely, if I plug f of x into g, I get back x, and if I plug g of x into f, I get back x, then g must be the inverse function. Okay, so this is like saying, this is like an if and only if statement, okay? If this thing is true, then it's the inverse function. And also, if f inverse is the inverse function, then this is true. Okay, so that is what happens when we plug a function into its own inverse. Okay, so by the way, one other thing that you could write is that f inverse is just f, right? If I invert the inverse, I get back the original function. So this is like a 2-way street. We actually say that these 2 functions are inverses of one another. Inverses of one another. Okay, so it's a equal relationship both ways. As relationships should always be, right? Okay. So let's try to apply this. Okay, so we want to verify that these 2 functions are inverses. And the way that I'm going to do that is using this last property. I know that if I plug f into g and I get back x, and if I plug g into f and I get back x, then I can conclude that g is in fact the inverse function. So we're just going to check this algebraically, and it'll be super simple. All I'm going to do is compute the composition. So let's start with g of f of x. Well, that's the same as g of, I'm going to replace f of x by what it's equal to, which is x cubed. And what am I going to do now? I'm going to plug x cubed in for x in the function g. And let's see what happens when I do that. I get the cube root of x cubed. What do I get when I do the cube root of x cubed? Just x, right? Okay, if you want to see why, you could also rewrite this as x cubed to the 1/3 power, right? And then you could use the exponent rule, which says that if I have an exponent to an exponent, I multiply the exponents, right? If you multiply the exponents, then what would you get? You'd get 3 divided by 3, which is 1. And x to the 1 is just x, okay? So that's another way you could see that. All right, now let's do the other way around. Okay, this alone, the fact that this is equal to x, is not enough to say that the two functions are inverses of one another, okay? We must also show it the other way around. We also need f of g of x. Let's see what that's going to be. Well, that's going to be f of, well, g of x is the cube root of x, right? So I get the cube root of x here. And now the f function just takes whatever I have inside and cube it. So we take the cube root of x, all cubed. And of course we get x again. So what can we conclude about these two functions? They are inverses. That is, g of x is equal to f inverse of x. Okay, that's another way we could say the same thing. G of x is equal to the inverse is the same as saying these two functions are inverses. Okay. Any questions on this process by which you can check if two functions are inverses? All right. Doesn't seem like there are, so let's do one more example real quick. Let's find the inverse of f of x equals x squared plus 5. Okay, now I have a question. Without this condition, if the problem was written as shown, what would be our answer? I claim that you can have an immediate answer. You don't even need to do any calculations. Well, what does this function look like? It's a parabola, right? Something like this. Is there any type of problem in finding the inverse of a parabola? Yeah, what is that problem? Yeah, Kevin hit the nail on the head. It doesn't pass the horizontal line test, does it? Watch this. Oops, it touches at 2 points. Can't find the inverse. But if I add this condition, the domain, we say the domain is just larger than or equal to 0, then we're talking about the function which looks not like a parabola, but like half of a parabola, yeah? And so it passes the horizontal line test. Is 1 to 1. Sometimes I'll write it like this, 1 to 1. Okay, why don't I write it out? That's confusing. 1, 2, 1. So it passes the horizontal line test. It is 1 to 1. I can go ahead and invert it using the process of, okay, I know y is equal to x squared plus 5. So what do I do to find the inverse? I replace y by x, and I replace x by y. And now I try to solve this equation for y. If I do that, then I get y squared equals x minus 5, and therefore y is equal to the square root of x minus 5. And I'll just quickly note that this, in the context of this problem, this is clearly referring to just the positive square root, right? Because all the y values should be positive, right? All the y values should be positive. Okay, in fact, every point on here has positive x and positive y, right? Okay. So that's what I want to say about that. Okay. Oh, that's why I was like so confused why this graph doesn't look right. It's because it should look like that. Jesus. Okay, that makes a lot more sense. Because I was thinking that this line, or this, okay, by the way, the graph, okay, of an inverse function will be the graph of the function reflected about the line y equals x. So here's the graph of the square root of x minus 5 is the square root of x with a horizontal shift to the what? To the right 5 units. Okay, so I go to the right 5 units, and then I draw something like this. Yeah? Okay. So, if you just turn your paper like 45 degrees, okay, so that it's diagonal, then you just reflect about that line to get the graph of the inverse. Okay. So that's the last one that I want to talk about for inverses. So we just need to make sure if we're going to find the inverse, we need to check the one-to-oneness property. And if we want to find the graph of the inverse, we just reflect about the line y equals x. And if we want to check if two functions are inverses, what do? We plug them into each other and we see if we get back what we started with. So that's pretty much all I have to say about inverses. Are there any questions on inverses before we move on to chapter 2? Okay, it doesn't seem like there are. So we're going to move on to chapter 2 here, which is going to start with something we've already talked about quite a lot, which is quadratic functions. Okay, so we've done an awful lot of factoring and quadratic formula and everything like that so far in this class, so what left is there to say about quadratic functions? Well, we can talk about their graph. Specifically, we can talk about their graph when we don't have real roots, right? So what if there's a parabola that exists just kind of like up here, right? How do we know how to graph it? Well, what we really need to know is what is the number a, so that we know how stretched it is. And also we need to know where is this vertex, which we call the point h comma k. So that's what we're going to go for next. So quadratic functions have this general form. I think I've reiterated that several times. We have ax squared plus bx plus c, where a, b, and c are real numbers. And the first one, a, should not be greater than 0. It should be not equal to 0. Sorry. Should be not equal to 0, right? Because if a is 0, then this whole term goes away, and the rest of this function would be what? Not quadratic, but linear. Very good. Okay, so let's talk about vertex form. The book calls this standard form, which I guess is really confusing because this is, I guess, what they call general form. But I feel like general and standard kind of, they sound too similar. like as words. For me, anyways. I guess general is like less, general in this context means less specific. So this is a specific form, which they call standard, and the general form is less specific, it's just general. Okay, whatever. We're not gonna mince words about words. So I like to call it vertex form. The reason I like to call it vertex form is you look at it and you can immediately see where the vertex is gonna be. Okay, so if I have f of x equals a times, and you put this stuff in parentheses here, right? X minus h, okay, x minus h squared. Then, what do I get? I get the graph of a parabola with vertex h comma k and also stretched by a factor of a. Okay, also stretched by a factor of a. So this a here is the stretch factor. What kind of stretch will this type of multiplication give us? A vertical stretch or a horizontal stretch? Well, let's talk about this number. Is this going to give us a vertical shift or a horizontal shift? Vertical, right? Why vertical? Because it is on the outside of the parentheses. And the number a is also on the outside of the parentheses. So it's also going to have to do with the up and down world. It's going to be a vertical shift, or a stretch. Okay, so that's the stretch factor. Then h is going to be the x coordinate of the vertex, and k is going to be the y coordinate of the vertex. And something a little bit confusing is, again, it's confusing for the same reason that it was confusing when we were doing circles, which is x minus h means that the coordinate of the vertex x value is h. So if it's like x minus 3, I'm not going to put a negative 3 here. I'm going to put a positive 3 here. So you got to flip the sign of whatever's in there, okay? But what's more confusing than circles is we mix and match. The k, we don't change the sign. The h, we do change the sign, okay? So just be a little bit careful about that. So let's see an example. Okay, so it's really easy to graph parabolas that are in vertex form. At least it's a lot easier to graph them when they're in vertex form than when they are in general form, okay? I shouldn't say it's easy. But let's go ahead and try this one. Well, if my inside here says x plus 2, then that's the same as x minus negative 2, yeah? Which tells me that my h value is negative 2, okay? And then how about this number here? What does that tell us? Yeah, to go up. So that tells us the k value, which is 12. Okay, so the vertex is going to be at negative 2 comma 12. So let's go ahead and draw that. Here's negative 2 comma 12. Maybe looks something like that. Okay, the next question I'm going to ask is, should my parabola open up or down? Okay, we all say down because of this big negative sign here, right? That negative sign is going to make us open down instead of opening up. All right, and then what's the effect of this 3? Is it going to get stretched or compressed if we have a 3 here? It's going to get stretched, right? So it's going to start looking like this, but if we stretched it, what would it look like? It would look more like this, yeah? Agree? So it should be steeper. In fact, how steep should it be? Well, you can think about this as a transformation, okay, of y equals x squared. So let's talk about what happens with x squared. Okay, what happens first is we start at 0, 0, and then when we go to 1, 1, right, because 1 squared is 1, and then we go to 2 comma 4, okay? So what happens is I move over 1, up 1. If I'm doing that, but stretch by a factor of 3, I should go over 1 and down how much? 3, right? Over 1, down 3. So over 1, down 3, so this would be the point -1, comma 9. And then, of course, I'm going to do the same thing on the other side. So this is the point -3, comma 9. Okay, then what? If I move over 2 units on x squared, how far up do I go? I go 4 units up, right? Because that's the square of 2. But I need to multiply that height increase by 3, or really by -3, right? So instead of going up by 4, I'm going to go down by how many? I'm going to go down by 12, right? Because that's what I get. I would go up 4, but I need to multiply that height increase by -3, which is how I get -12, which means go down 12. So then I would be at 0, 0, and -4, 0. Okay, so this parabola looks something like that. Obviously not to scale, but you can get some points on there. Okay? So that's how I would graph it in vertex form. The most important thing is that we put the vertex where it needs to go and it's opening in the correct direction. From there, you know, if you want to add some extra points, probably that would be a good thing to make sure that you draw it reasonably to scale. I would say going over 1, going over 2, that's probably enough. And you only need to do it in one direction, right? Because it's symmetric. Okay. Any questions on that problem? Yes.
Can you go over how you got the bottom 2 points again, the 0, 0, and the -14?
Sure. Okay, so the way I'm doing it, okay, is I'm viewing this as a transformation of the function x squared. Okay, I'm viewing it as a transformation of the function x squared. Okay, so remember when we learned transformations, we learned, well, if you add something to the outside, that represents a vertical shift up that many units. If I add something on the inside, that represents a horizontal shift to the left by that many units. Okay? So where did I start? I started with a picture which looks like this, and I transformed it into this by doing the following process. The first thing I did was I moved it over to the left 2 units so that it would look like this. Then the second thing that I did was I applied the vertical reflection, right? Which made it look like this instead. And then what did I do? I applied the vertical stretch, which was a factor of 3. So that made it look like this. And then what I did was I moved that all up by 12 units so that it would go up to here. Okay? So that's where it all comes from. But in terms of how to find these points specifically, what I need to understand is that when I move a parabola around, the relationship between how far apart these points are in terms of their height will be preserved up to this vertical stretch. So I know that if I were to go from the vertex to 1 point over from the vertex, on the normal graph of x squared, that means I go up by 1. But since I have a vertical stretch by 3, what I need to do is go over 1, and since I stretch by 3 vertically, instead of going down 1, I'm going to go down 2, 3. Okay, because of that 3 there. It's affecting the output, basically. So the relationship between the heights of these 2 points will be preserved up to a factor of this stretching. Does that answer your question? Okay. But if you want to plot some points and you don't necessarily have to view it that way. What you could do is find out where the vertex is, And then if I wanted to know what is the height of the point where x is -1, I could also just take -1 and plug it in. Okay, that would be an easier way maybe to do it. I could plug in -1. It would take longer, but you could do it that way too. And then I would plug in 0. If I plugged in 0, what would I get? I'd get -3 times, this would become 2 squared. So this would be -3 times 4, which would be plus 12, which would be -12 plus 12, which would be 0, yeah? So that's how I could get the height of the point here, by just plugging in the x value into the function. Any other questions on that? I thought I saw another hand somewhere. Okay. So if not, then let's talk about the most difficult part of today's class, I think. Everyone's laughing like it was already hard, right? Is that the point? Okay, yeah. Well, this is the trickiest part. Okay, so what have we learned? We have learned that it is relatively it's not easy, but it's a lot easier to graph a parabola when it's in vertex form. So the next question is, what the hell am I supposed to do if it's not in vertex form? How do I graph it? Can I still graph it? The answer is yes, of course we can. We just need to convert it into vertex form first, and then we'll know how to graph it. Okay? So let's see how we do that. So we start with something like ax squared plus bx plus c, and we want to turn it into something like a times x minus h squared plus k. Okay, now this should remind you a little bit of what we did with circles, right? This should remind you of what we did with circles. We had something in like a all expanded out form, and what did we have to do with circles in order to get something like a perfect square here? We had to complete the square, which is what we're going to do again here. Okay, so let's take it step by step. The first step is to factor out an a from the first two terms. Okay, I'm going to leave c all by itself. So we leave c alone, but we take out an a. So what I'm left with is just x squared. Okay, that's why I took out the a. But if I take out an a from these first two terms, I got to remember that if I take an a out from bx, I get b divided by a times x. Okay? Because if you were to distribute this a onto these two terms, we would get back ax squared. And if we did a times b over a times x, we would get just bx. Yes? Okay, so I take a GCF out of a. Then what do? I'm going to complete the square. What do I do when I complete the square? I take this number, I divide by 2, and square. So I take b over a, I divide it by 2. What would I get? b over 2a. Then b over 2a squared would be b squared over 4a squared. Should have a square here. Okay, this is going to be more clear when we work on an actual example. All I'm doing here is completing the square. I'm taking the requisite number here. I just divide by 2 and square. Divide by 2 and square. Then I'm going to add that number, and I'm going to subtract that number. And now what I want to do is, this guy should be in the perfect shape that I can make a perfect square, right? Okay. I think it's confusing because I'm using letters here and not numbers. We'll see an example in a minute with numbers. Okay, so let's finish it off. All we do is we take this guy and we factor it into x plus b over 2a squared. Okay, x plus b over 2a squared. And then we have to resolve the remaining minus, right? So we just move it out, okay? To move it out, what we have to do is first multiply by a, okay? So we get 4a here is what we should have. Okay, and then now we have it in the right form. A number times x plus something squared plus another number. Okay, so whatever this is going to be minus h, and then whatever this is going to be our k, and that's how we get the vertex. So we're not going to try this with a partner. We don't have quite enough time. I'm gonna run through this example of how we do it. Okay, so I'm going to go through the steps one by one. The first step that the notes tell me to do is to factor out whatever this a value is. We take it out of the first two terms. So let's do that process first. Well, I'm going to start with 2x squared plus 8x minus 10, and I'm going to factor out this 2 from the first two terms. If I do that, I get 2 times x squared plus 4x. Agree? So now my game is to complete the square inside these parentheses. So what should I do if I want to complete the square for something like x squared plus 4x? I should add and subtract something, right? What do I add and subtract? Well, I can't quite factor like that because I have this x here. What I need to do is add and subtract something first so that I can factor. So I have like ax squared plus bx, right? What am I supposed to do when I complete the square? I take this number, divide by 2, and square it. Yeah? So I take 4 divided by 2, all squared. That's the same as 2 squared, which is 4. Yes? Let me make that a different color. So I'm going to take that number, and what am I going to do? I'm going to add it and also subtract it. Yeah? So this number went, this number went here and here. So it's the exact same as when we did it for circles, okay? We take that middle number, divide by 2, and square it. We add that number and subtract it. Now, this whole thing is what? It's x plus 2 squared, right? So this is 2 times x plus 2 quantity squared. And how am I going to deal with this extra minus 4? I'm going to add it to the 10, but first I have to multiply by 2. So I'm going to get minus 8 minus 10. Okay, minus 8 minus 10. So I get 2 times x plus 2 squared minus 18. Okay? So I think it's a lot less scary when you see it like this. So yeah, we'll stop there for today.